Hello class, this is Adam Ward, and I want to work with you on a problem where we're using the Moody diagram to estimate major losses, or losses due to friction, through a pipe flow network. This is what I describe in class as a type 2 problem. In this case you're given both fluid properties and the pipe geometry, or more generally the problem geometry, and the key unknown is some flow property, be that velocity or discharge. In this case, we're given a pump that's moving water from the lower reservoir on the left to the upper reservoir on the right, and the objective is to find flow rate in the pump. These problems get confusing because to estimate discharge, we need to know the velocity. Velocity in turn requires that we'll know head loss and be able to solve the energy equation. To estimate head loss from the Darcy-Weisbach equation, we know that is a function of both the friction factor F and the velocity directly. Friction factor is a function of Reynolds number itself is a function of velocity. So to get the unknown, you have to know the unknown. And so this puts us into an iterative solution. And so we'll walk through an example here of how to do this. One thing we'll need to use the Moody diagram is that ratio of the roughness length epsilon to pipe diameter, calculated here as 0.0017. And then our strategy will be to establish points 1 and 2 at the water surfaces and apply the energy equation from point 1 to point 2. And so you can see I've written out the full energy equation to describe the flow path illustrated on the left. By choosing the points that we've selected, pressure at the water surface we can assume to be 0, velocity of 0 in the reservoirs, and if we assume that Z1 is equal to 0, so we set our datum at point 1, we can zero that out as well. A couple of simplifications or assumptions we can make along the way here. One is to use the Darcy-Weisbach equation to replace that head loss term, and the second will use our equation that describes pump head as a function of the rate at which work is being done, divided by efficiency times specific weight times discharge. So simplifying the equation, we end up with this, and I'll go ahead and plug in some values that are given in the problem. Notice that we're converting from horsepower into pound-feet per second for the pump term, and then the second term, the Darcy-Weisbach portion, friction factor F I'm just leaving in there as an F for now, and I've written everything else out except for where we would normally put velocity squared. To simplify this problem, we can recognize that velocity squared is discharge over area, that quantity squared, and so we'll go ahead and plug this in as Q squared over A squared, and what that gives us is this equation that's only got the unknowns of discharge Q and friction factor F. From here, we find ourselves in the domain of this iterative solution, and so I want to walk through how this actually works out. Step 1 here is to get our Moody diagram, identify which of the lines that we're actually working on, and we're going to start by initially just taking a guess for the friction factor F, and so I'll pick a value of 0.030, about the middle of the range. If that were the friction factor F, we can solve the energy equation written above, and I solve that equation for a discharge of 2.05 cubic feet per second and a velocity of 10.44 feet per second. So we've made a guess for F, we've solved the equation, and now we're going to check and see if our guess was a good guess. Now that we have a velocity, we can calculate a Reynolds number. I get 4.31 times 10 to the 5th. And we take that Reynolds number and go to the Moody diagram. So we locate that on the x-axis, read up to the line that describes our relative roughness, read directly over to the y-axis, and I get a friction factor of about 0.022 based on my read of the chart. This is where the iteration comes in. That friction factor is not what we guessed, and so our guess needs to be updated. So we can go through, erase the terms we just calculated, and start again with a friction factor of 0.022. Repeat the process by solving for discharge, velocity, by calculating a new Reynolds number of about 4.69 times 10 to the 5th, And we go back to the Moody diagram again, read up to our relative roughness, read across, and for the resolution that we have on the Moody diagram, I'll argue that we end up with the same value of f. So what we started with equals what we ended with, 0.022 again, we're done. If you were to read a different f, you would simply repeat the process of iterating until you converge on a solution, where the guess for f and the calculated f from the diagram match one another. As you go through this problem, one tip to point out, if you take this energy equation and you solve it in the form so that it's discharge as some function of the friction factor, that'll save you some time and some button punching on your calculator because you're going to be iterating through that calculation step multiple times. I hope this helps you see how to solve a type 2 problem. The other type of problem that you'll use a very similar approach for is what I call a type 3 problem in class. That's when you're given something about the fluid properties and the flow properties, and you're actually after the pipe geometry. So that type of problem would be recasting this exact same question, but perhaps asking for a given flow rate of 7 cubic feet per second, what would the required pipe diameter be? You're going to use a very similar approach where your unknowns will be pipe diameter d and friction factor f. You'll guess f, go through the calculations to solve for d, use that to go to the Moody diagram, and iterate through on f. I hope you find this video helpful, and best of luck with the Moody diagram. Thanks.